On tonight's show, Dallas blows the budget in Vegas. I'm in Iceland checking out the infamous volcano that grounded all our planes.
It's seriously like being on another planet.
And Jem is in France breaking glass. That's Bang Goes the Theory, putting science to the test.
It's magic.
Hello and welcome to Bang Goes the Theory. Now, you may remember back in April, the airspace of Britain pretty much emptied out thanks to a massive cloud of ash that erupted from Eyjafjallajökull, that infamous Icelandic volcano. Now, it had a massive impact on us back then, and there's no guaranteeing it won't affect us again. So I went to investigate the might of Mother Nature for myself. Just over there, in the distance, I can see the top of the volcano and this massive, thick, black plume of volcanic ash coming out the top of it. Even from this distance, it looks pretty awesome. At this time of the year, the 2-hour drive from Reykjavik should take me through green pastures, but not this morning. The land has totally changed.
We're not in Kansas anymore.
The larger particles of ash fall closest to the volcano, turning the land grey. The lighter particles are caught by the airstream and head east towards Europe.
I can't see more than 100 yards ahead of me. It's like some kind of Armageddon or something.
Eventually, I can't resist venturing out into the desolate landscape.
Unreal. It's seriously like being on another planet. And I can't imagine what all this ash is doing to the environment and to the farm animals and to the people who live here. It's this fine layer everywhere, and beneath my feet, it feels like snow. It is incredibly gritty. It's very harsh. Yeah, I'm getting out of here.
Finally, we get upwind of the volcano and suddenly the land is green again.
Look, 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 guys. Oh my gosh, look at that.
There it is, the most notorious volcano of the decade in all its glory. Unbelievable. I don't know about you, but that looks pretty active to me. We're about 8 kilometers from the volcano, and the erupting rocks might look small, but the largest of them are actually the size of a car. The real danger here is when ice at the top of the volcano melts, and the resulting meltwater makes contact with the magma, which shatters into fine ash that blasts over 10 kilometers up into the air.
Oh my gosh, that's new, that's black and nasty.
This is a powerful reminder that we know more about the surface of the moon than we do about the earth beneath our feet.
Even the fact that the continents move has only been common knowledge for a little over a generation. But here's what we do know. Imagine if this plum is planet Earth. Now, if I cut it in half, what you basically have is a cross-section of the inside of the Earth. Now, the outer layer is called the crust, which includes the continents and the ocean floors. For example, the continent of Europe might have a crust that's 50 kilometers thick, whereas the Atlantic Ocean around Iceland here might have a crust of only 10 kilometers thickness. Inside the crust is the mantle. Now, the mantle is super hot rock. It goes all the way down to 2,900 kilometers below the Earth's crust and is made up of about 40% silica, the same stuff that glass is made of. Now, inside that again is the Earth's core, the very center of the Earth, going down to 6,370 kilometers below the Earth's surface. It's made up largely of iron and is even hotter than the mantle.
It used to be thought that the mantle is molten rock, which rises to the surface and erupts from volcanoes in the form of magma. And when you look at the magma spewing from this volcano, that seems to make sense. But the mantle is in fact solid rock that only melts under very specific circumstances, especially below the edges of the tectonic plates that make up the Earth's outer layer.
Iceland is slap bang on the middle of a constructive plate boundary. This is where the European tectonic plate meets the North American tectonic plate. These two plates are moving apart ever so slowly, a couple of centimeters every year, about the same speed as the growth of your fingernails. But why does the mantle melt when it's drawn upwards into the space created by the plates? Basic science states that if you reduce the pressure of anything, its melting point will also be reduced, or its boiling point. It's the same idea, so I'm going to show you with this hot water. Right, the temperature of this water at the moment is 85 degrees Celsius, okay? Now the boiling point of water is 100 degrees Celsius, so clearly that is not boiling at the moment. But if I reduce the pressure inside the flask, check that out. The pressure inside the flask has been reduced and the water is boiling at 85 degrees Celsius. The pressure inside there is lower, therefore its boiling point is lower as well. And that's pretty much what's happening with our volcano and the mantle beneath it. As the tectonic plates that split Iceland in half move apart, the mantle is slowly moving upwards. As it moves upward, the pressure is decreasing, and as that pressure reduces, the melting point of the mantle reduces also, which means the mantle, the hot solid rock, begins to melt into molten magma. Every inch of Iceland has been formed by volcanic eruptions. The tectonic plates moving apart, the pressure dropping, and the mantle melting, allowing magma to spew to the surface. But it's not only magma that makes some volcanoes so spectacular. Gas can also play a part. If there are also gases dissolved in that magma, then as the magma rises, the pressure decrease is going to cause those gases to exsolve out of the magma, forming massive gas bubbles. And if the conditions are right, for example, if the magma is viscous enough, if it's nice and gloopy, then the pressure is going to build up in those bubbles until eventually it's going to explode the magma out of the volcano. A bit like a bottle of pop.
Wow, good film, really good film. Okay, a couple of things I want to know though.
Yep.
Thing one, is it still going off?
No, not at the moment.
Thing two, is it going to go off again?
Well, the last time it went off, back in 1821, it went through a resting phase a little bit longer than this one, and then it went off again, and it was basically active on and off for 13 months, so there's always a possibility.
So it still could go off again?
Yeah.
Third thing I want to know is Katla, the other big volcano.
Yeah.
What are the chances of that kicking off?
Yeah, it's only 50 kilometers down the road from this volcano. It's got a magma chamber 10 times the size of this one, and the really interesting bit is every time this volcano has gone off, or at least the last 3 times, Katla has always followed. Now, we don't know enough about the geophysics to understand whether that's just a coincidence or whether they are actually linked, but we need to watch this space, don't we?
Yeah, we certainly do.
Yeah, if you want to find out more about the Icelandic volcano situation, we've got an in-depth interview. All you have to do is follow the links to the Open University from our website.
Yep, all the details are going to be up there on /bang. Right, now coming up, something we're all pretty rubbish at, and that is the way our brains weigh up statistics, probability, randomness and chance. Working out probability is a pretty exact science, but the results can seem very odd. Where better to demonstrate that than the gambling capital of the world, Las Vegas. It's all kicking off in Vegas. This is Akash, he's from Orange County, he's quite good at maths. Now, there's a dollar bill under one of these cups.
Okay.
Okay. Now, just off the top of your head, what would be the odds, just by picking one, of finding the dollar bill?
1/3.
Exactly right, 1/3. So what I'd like you to do is to point to a cup where you think the dollar bill might be.
The middle one?
The middle one. Okay. I'll tell you what I'll do. I'm going to make it even easier for you. I'm going to show you a cup that's definitely not under. So we're down to these 2 cups. I'm going to give you the opportunity to change your mind.
All right.
So you can either stay with that one, or you can change your mind to that one.
Okay. I'll stay with it.
You're going to stay with it, you sure?
Yeah.
Last chance to change your mind.
I'm going to stick with it.
Now that might seem odd to you, but calculate it mathematically and you'll find that by changing the cup actually increases your chances of winning from 33 to 66%. But I agree, on a gut level, it just seems weird. And that's the strange thing about probability. Often seemingly improbable things are, mathematically, highly probable. Okay, let's try this. Now, there's about 25 or so people eating in this restaurant. What do you think is the probability of two of those people actually sharing the same birthday? Well, come with me, I'm going to find out. Can I just ask you a few questions? Is that okay? I'm doing a little probability experiment. How many people do you think you'd need to have in a room to get an even chance, a 50-50 chance of two people sharing the same birthday? Ballpark.
I would say 50 people.
Anybody else? What would you say?
About 100.
About 100? Oh, you look really worried. Okay, to be 100% sure, I need 366 people. One more if it's a leap year. But what about a 50-50 chance? Okay, we're going to play a little game of birthday bingo. We're going to go around the tables and you're going to shout out your birthday. So if you hear somebody with your birthday, you can shout birthday bingo. Okay, here we go.
September 7th.
September 7th.
November 12th.
November 12th.
May 26th.
May 26th.
November 15th.
November 15th.
January 29th.
January 29th.
July 29th.
July 29th.
March 16th.
March 6th.
That's my birthday.
Birthday bingo. let's break out the ID.
All right.
And there you go. The driving licenses prove it's no lie. Both are born on March the 16th. This is Anna.
We have the same name.
Really?
You have the same name? Okay, that is weird. That is really unlikely. Luckily for me, there's someone clever here who can explain why this odd result is so probable. This is Deborah Nolan, who's a professor of statistics at the University of California, Berkeley. Mm-hmm. Is that just a really weird thing that just happened? Given there's only 25 people in the room, two shared a birthday, to me that seems really odd. I would have thought you'd need a lot more.
It's not so weird, actually. It's actually 50-50 with just 23 people in the room.
But why? I mean, that seems really counterintuitive.
Well, if we take you and me,
yeah,
and the chance that we share a birthday is about exactly 1 in 365.
Yeah.
But then there are all these other pairs in the room. So I could pair with you, or you, or you. And so altogether, there are 24 pairs for me. And then there are 24 pairs for you. And so if we count up all the pairs in the room, with 25 people, we get 300 pairs.
In fact, Professor Nolan reckons that even something as simple as tossing a coin 100 times will throw up some unexpected patterns. It's not rocket science to assume you're roughly going to expect 50 heads and 50 tails. But does that mean you're very unlikely to, say, get 6 or 7 heads or tails in a row? That's what I'm going to find out. So we got half of our volunteers to flip coins 100 times and write down the results, and the other half had to imagine they were tossing a coin and write down what they thought the results might be. We then gave the results to Deborah to see if she could spot the difference between real randomness and imagined randomness. Right, one of these is real, one of them is
fake.
Guessed. Ready?
Ready.
Here we go.
Just.
Can you tell the difference?
Let me see.
What we need is a sort of loud ticking clock, just to sort of ramp up the pressure.
All right, I'm ready.
Wow, that was quick.
Yeah, I will say real flipper, guesser.
Okay, last one. Lynn? Yes. Is that you? Were you really flipping the coins?
I was really flipping.
Okay. Paul Jasper?
Yes, I was guessing.
That was amazing.
I got it.
Random crosses on bits of paper. How on earth can you tell the difference between people who are actually flipping a coin and people who are just guessing the outcome?
Well, people who are guessing usually think that you can't have too many heads or too many tails in a row. And so once they get up to about 3, they go, oh, the next one must be a tail. And so it flips back and forth with lots of little short runs.
See, this is interesting. Right. So this one, Lynn here, has got 8 heads in a row. Now that seems unlikely.
It made me a little nervous. I thought somebody might be trying to fool me.
But is that, I mean, having 8 heads in a row, presumably that's got to be fairly unusual.
Not so unusual. Randomness tends to actually come in bunches and clumps, and most of us don't think of it that way. They think it's got to be kind of evenly spaced, and that's how you can tell this. These are like 3, 2, 2, 3s, nice and evenly spaced, whereas this one has clumpiness, 8, 5. That happens when things are truly random.
I think that stuff's really interesting because it says a lot about how our brains see the world, because we tend to let our emotional selves get in the way of us seeing what is ultimately simple mathematics and probability.
Yeah, absolutely.
As I'd like to demonstrate with my probability machine.
Where on earth did you get that from?
I built it a long time.
This?
Me and a mate built it back in '95.
It's awesome.
Well, the idea is we shoot balls up to the top.
Yeah.
Now, every time a ball hits a pin, there's a 50-50 chance of it going left or right. You could never guess the path of any one ball. Yet, every time they drop in to form this curve. And it's knowing that kind of mathematics that allows bookmakers, insurance brokers, people like that to make a lot of money. It's all about being emotionless with statistics.
Wow, that is really interesting. And speaking of interesting things, it's time for more of Dr. Jan and his street science, available without prescription. And this week, he's determined to get everybody extremely wet.
Here you go. Can you hold that tray for me?
I can.
And I'll put a cup on it,
Yeah.
a glass, and fill it full of water. And now what I'd like you to do is just swing the tray a bit from side to side, okay? Like that. Yeah. Now, do you think you can get it all the way over your head?
In a word, no.
Go on, try it.
No, are you joking?
Go on, try it. Okay, now, oh, even like that, right the way around your head. Very good.
Go, Hattie!
But the weird thing is, you think it sort of defies gravity when it's at the top there.
Yeah, I don't understand why it wouldn't fall.
Yeah, but what's really going on is that it's going round fast enough that gravity doesn't have time to cause any problems.
It's so weird looking at it.
It doesn't feel like it should do that, does it?
It really doesn't. It seems strange.
So what do you think it is that's keeping the glass on the tray and the water, what's stopping the water coming out?
My skills.
Yeah.
Yeah, personally.
Is it the force of how fast it's going around?
Centrifugal force.
Ah, well, lots of people say centrifugal force.
Yeah.
The interesting thing is that centrifugal force is just a human invention designed to make the calculations easier. And in fact, it's actually called a fictitious force, and I'll show you why. Start swinging yourself around. How fast can you go?
That's so true.
You see, there's some sort of. It feels like there's something pulling you out.
Yeah.
Now, if I were to let go, if we're going really fast, and I were to let go about there, yeah, what would happen?
I would fail.
Yeah, you'd fly off that way, yeah? And that's just known as Newton's first law of motion, which basically says that once an object starts moving, it just carries on going in the same direction in a straight line, unless something gets in the way, of course. That's exactly what you're feeling here. So there's no real force flinging you outwards, it's just that because you're moving, your body wants to go in a straight line. When something like this is moving around in a circle, then there must be not a force going outwards, but there must be a force inwards pulling it in, and that's called centripetal force. Okay? For you, it was you holding on to each other. Yeah, that was the force. But for example, when the Earth orbits the Sun, it's because there's a centripetal force, gravity, that pulls them together. But in this case, it's the string doing the job of gravity. There's enough tension in the string to generate that sort of inwards pulling centripetal force, and that's why it's going round in a circle, and the glass on it and the water in there are all going round in a circle and not flying off in one direction.
See, that's another great bit of science that almost defies logic, but totally works.
Yeah, absolutely. He's probably not going to make it as a waiter, though.
Yeah, good point. If, like me, you just can't get enough of Dr. Jan, there's more of him on the website, as always. Plus, he's going to be answering your questions live in a very special Red Button show next week, so get your questions ready. In fact, it'll be your chance to talk to all of us live in the studio and ask us anything you like about the show. Or even come up with a crazy contraption for Jem to build next series.
Terrifying thought.
Right, next up, the power of the sun. When I got the opportunity to visit one of the world's largest solar furnaces, I knocked myself up a cheeky experiment and caught the next plane to the Pyrenees. As every school kid knows, you can use a magnifying glass to focus the sun's energy and set fire to things. Although it's not something you should do in a forest. But have you ever wondered how much energy you can get from the sun? Well, the British astronomer John Herschel wondered exactly that back in 1838. And he came up with a very simple experiment to figure it out. All he needed was a pot of water and a thermometer in the shade of an umbrella. He left the water until it had risen to the same temperature as the air around it. Then he could remove the umbrella and expose the water to the direct rays of the sun. He then measured the time it took for the temperature of the water to rise up by, say, 1 degree. From that, Herschel was then able to calculate the exact amount of energy from the sun's rays that were being absorbed by his pot of water, and therefore work out the energy per square metre falling on planet Earth. It turns out that in the middle of the day, the power hitting the top of that pot is roughly the same as it takes to run one of these light bulbs, about 1 kilowatt per square metre, which, if you could convert it all into electricity, means you could practically carpet the planet with these and power them all from energy beamed in from outer space. So how can we tap into that power spread out across the planet? Well, one way is to concentrate it using mirrors. So if I'm able to bounce 60 watts of solar energy off here onto something, and then bounce another 60 watts to the same place off this mirror, I can make an area with double the power of normal sunshine. And they do exactly that on a larger scale here at the Solar Furnace Research Facility in southern France. Bolted to one side of the main building is a 9-storey high concave mirror. And they have a cunning way of following the sun as it moves across the sky.
We have in the field 63 heliostats.
So by heliostat you mean something that tracks the sun?
Yes, exactly. Yeah. It's computer control. Computer calculates where is the sun, and when we did the heliostat, it calculates how to aim it to send the energy towards the parabola.
The parabola's job is to focus the sunlight. So you have a whole field out there of mirrors that are kind of collecting the sunshine, then they broadcast it into your big dish.
Yes.
And then the dish focuses it down to that minuscule little point over there.
Yes. We have about 2,700 square meters of parabola here, and right now we are working on 4 centimeters wide sample.
The power focused on that tiny point is equivalent to more than 1,000 microwave ovens. Emmanuel takes me to demonstrate what solar power can do by using a much smaller parabola, which used to be a German searchlight reflector from World War II. How tight does this focus? Can we see it?
Just look, yes. By spraying some water.
Oh my God. So if my hand's here, it's okay, but if it went there, what would happen?
Not at the focus. Here it's okay, but...
And even a mirror this big, would it be powerful enough to kind of set light to something?
Yes.
Can I try it?
Go ahead.
Okay, show me the focus. I'm okay. Oh, my life. Can we do that again? That's astonishing. I've never seen anything set light to wood that quickly. How hot is it in there? What temperature does it get to?
At that focal point, we can reach a temperature higher than 3,500 degrees C. And there is currently no known materials that could resist this.
There is nothing on Earth that can withstand the temperature right in the middle there?
Nothing.
And I'm pointing at it.
Exactly.
Just 2 square meters of sunshine can melt steel pretty easily. I would love to try and weld some stuff with sunshine. It'd be really nice. If you had 3 people sunbathing, they would be collecting that amount of sunshine. And look what it does. Despite having travelled 93 million miles, the energy of the sun can even melt rock.
Look at that!
See, to me, that's far more amazing than melting steel. Like, I see steel melt every other day, but I've never seen anything like that. I'm simply astonished that sunshine will melt rocks. It just doesn't seem right. It's certainly impressive, but can we get anything practical from the sun's energy? Time to get out my travelling workshop. Okay, what I've got here is hopefully a solar-powered steam rifle. In that, I'm going to put some water in this chamber here, heat it with my concentrated sunshine. If I can get it to boil, or above 100 degrees, that pressure gauge is going to start going up, because the pressure in here will get higher and higher. When it gets high enough, maybe 3 or 4 atmospheres, I can then open this. The steam will drive its way down this pipe, so if anything's in that barrel, it's going to get driven out pretty hard. And it'll be like a solar-powered rifle, which is a good thing, if used in the correct way. This is not just a pointless gimmick. This is actually how solar power stations could work. Instead of using that high-pressure steam to drive a potato down a barrel, it could be driving the blades of an electrical turbine, generating clean power. Having assembled my rifle, I borrow one of their parabolic mirrors. Now, if I had to get this like bang in the focus, there's a danger I would just melt straight through that copper pipe and we would have a giant steam accident, which nobody wants. Copper plumbing pipes should be fine. It takes surprisingly high pressures, but I'm dealing with some pretty extreme temperatures, like that. I can't let it get the full force of the sun. Still, the pressure builds up astonishingly quickly. Ooh. 3, 2, 1. Oh! That's well over the trees! To confirm that it's a reliable method of power generation, I try it again. Ready? Oh! 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 Nearly had to call the glaziers then. And there it is, boiled granite.
Oh my God, that is amazing, isn't it? Look at that.
It is awesome.
It's so fragile.
And that's what happens just from concentrating 2.5 square metres of sunshine into a space that big.
Amazing. Right, we are out of time, though, so what are we doing next week, boys?
OK, well, I am off to deep space to look at the life and death of a comet, those great dirty snowballs of frozen dust and ice that whiz about.
Excellent. And you, Jem?
I'm playing with ice too, but as it's the last show in the series, I'm really going to push the boat out, quite literally.
In what way, then? Explain a little bit more, please.
The plan is to build a boat made of ice that the 3 of us can set sail in.
OK, and because of that, I'm going to get myself prepared by getting repeatedly dunked in cold water. It may sound bonkers, but there is a good scientific reason for it, I promise. We will see you next week. Say goodbye, boys.
Goodbye.
Bye, boys. I can't believe I said that, Jag.
Coming up next this evening, we're off to Waterloo Road, where Ruth has an unfamiliar experience. Then at 9, Alan Sugar meets 16 business-savvy hopefuls, all vying for a chance to be the next apprentice.
That's astonishing.